All right, pre-calc, we're going to jump to 4.8, simple harmonic motion. And what we're going to talk about here is either sine or cosine. And we have a couple of things change, right? We say have A is the amplitude. But omega, this curly W, that means we're going to talk about when omega is greater than 0. And when we have that, the frequency, so this is talking about the number of times something, may go back and forth. It's kind of like period, but not exactly. So we'll deal with that in that way. So that's omega divided by 2 pi. Okay, so no, our omega is technically the b value, right? So that's what we had been using as 2 pi divided by. So this one's going to be that reciprocal function to work with that. Okay, so how do I know which one to use? Okay, so if we have 0, 0, that's sine, right? Because sine starts at 0, 0. So if it's at equilibrium when we get started, or if we can identify 0, 0, then that's what we'll use. If it's not at 0, 0, we're going to use cosine, because right? Cosine starts typically at 1, right? It's reciprocal is going to start at -1, so we have those. So if it's above or below, when it's at its resting point, then that's what we're going to deal with. State of equilibrium, resting point of the oscillating object. So whether it's a piston, a spring that goes back and forth, the maximum displacement, that's the amplitude. Okay, the period is the time it takes the oscillating object. Okay, and then the frequency. So this is the one that gets tied together. So here's what we're talking about, that reciprocal. It's 1 over the period. Okay, and that tells us how many cycles the oscillating object does per unit of time. If that's per minute, per second, think about the revolutions per minute for something in an engine, those type of things. Okay, so we're going to try and build up the vocabulary, but here are the things that we need to be able to do with it. Okay, so we want to find the amplitude. Well, the amplitude is kind of the same place it was, right? So the amplitude is 2. All right, we want to find the period. Okay, so the period is going to be 2 pi divided by pi over 2. Well, what's that mean? That means 2 pi is over 1 times 2 over pi. Right? So all we did was made this into a complex fraction. And we're going to reduce that. Pi's cancel out. We get 4. Okay, so that means the period turns out to be 4. Well, how do I find the frequency? The frequency is going to be 1 over the period. So it's going to be 1/4. Okay, there are no units in this one. Okay, so we have the period and we have the amps of 2. Okay, so very similar to what we had been working with just to get started here, and then we'll get some applications here in a little bit. So we have a leaf floating in some water here. And here's our equation, 5 cosine 3 pi over 4t. So let's pull some things out here. We want to find the maximum displacement. Okay, so the maximum displacement is going to be the amplitude, which is 5. We do have a measurement this time in centimeters. Okay, so we have this one checked off our list. So the frequency is omega divided by 2 pi. Okay, so we're going to take 3 pi over 4 and divide it by that 2 pi. So that's times 1 over 2 pi. And our pi's cancel out. We got to a 3/8. 3/8. Okay, so our frequency is 3/8. So that means we're going to do 3/8 of a cycle per second. Okay, because this was time measured in seconds. Okay, but this one's not going to be based in centimeters, right? So it means it's going to bob up and down 5 centimeters, but in 1 second, it's only going to move 3/8 of that. So we start getting a picture of what's happening. All right, and kind of go in reverse now. Can we write the equations? Can we write our equations? Initial position. Okay, so 0. So that means I can identify 0, 0. What's that mean? Which function starts at 0, 0, and that's sine. We have an amplitude of 4, so now it's 4. Right, and then the next thing they tell us is the period is 6 pi. Okay, so that means I have 6 pi over 1. That would have to be equal to are inverse, right? Because the frequency using omega is the inverse of that. So I'm going to use 2 pi over omega so that we can solve. Okay, so this, we're using the inverse, because we're trying to get to omega, but frequency is supposed to be 1 over the period. I don't want to switch that, so I'm going to flip-flop the other side as we work with that, because usually it's going to be omega divided by 2 pi. So I hope that makes sense. Otherwise, we'll kind of talk about it in class like we normally do. Let's cross multiply. 6 pi omega equals 2 pi divided by 6 pi. Pi's cancel out, so we got omega is 1/3. So that means we can go back up here. We could say 1/3 the amount of time. Okay, that's all we're kind of working with here. Okay, so initial position, just to kind of see these side by side, I think is nice. Cosine. And we're going to start off with the amplitude of 5, but notice it's starting at -5. So I do want to change that sign there. And now the period is 8. So we're going to work with exactly the same thing we just did, right? So I get 8 over 1 equals 2 pi over omega. If I had fancy handwriting, I'd make that look curly like a W, but really I'm solving for W in this problem, right? So 8 omega equals 2 pi. We're going to divide by 8. So omega turns out to be pi over 4. Okay, I just want to make sure we had kind of both of these. It does not have to always turn into a number like 1/3, pi over 4, and we're talking about t as we go to write these. Okay, so I could say, you know, the function based on time is equal to, for both of these, the function based on time, and you'll see why I'm using time here in just a minute. Okay, so those are our basics of what we're trying to do. So what are a couple problems that we're going to look into, right? Like I had mentioned, we're talking about maybe a piston in an engine, something like that. So here's our first one, and the other one, maybe talked about it in physics class. We talked about a spring and how it moves. Right, so a lot of stuff going on here. So take a look, see what's going on. We have an 8 centimeter radius turns. We have an angular velocity. Right, what's the frequency? Okay, so we have a lot of different things going on here. Was the distance from the starting position when time equals 0 exactly 3.45 seconds after starting? Okay, so a couple things we want to look at is initial position. When time is 0, we're at A. Now, I wasn't able to write 0, 0, so I know it's going to deal with cosine. So time equals 0. We got 0A. That means we're going to talk about cosine. All right. Let's get a couple things worked out here then. We know 8-inch centimeter radius. So eventually we're going to fill in 8 is going to be that amplitude as we work back and forth with those. So let's get some other information so we know how to fill in the rest of it. Let's get this. I'm going to go back to this angular velocity for just a second, because that tells me that I can actually turn this into a frequency, right? But 8 pi radians per second isn't something that we like to use right now. So for part A, here's what we're going to use. We're going to use 8 pi radians, factor label, per second. I want 1 revolution. Remember, 1 revolution was 360 degrees, but in radians, it was 2 pi radians. So I'm able to reduce these items. So pi takes out pi, I get 4, 1, so I get 4, and what's left is revolutions per second. Okay, and what that means is we're talking about a cycle. What it also means is that the period is 1/4. Okay, right? Because if this is inverses, so we're going to use 1/4 for the period. So that's going to help us spill into the next one. So remember what we did with the period last time. We said 1/4 equals 2 pi over omega. Okay, so we're going to cross multiply. Omega equals 8 pi. Omega equals 8 pi. I don't know why I wrote that a second time. But we started building the equation up top there, but now we can actually finish it out. So we had 8, right, because it was based on our radius here. Cosine. And we can tell that our initial position was on the positive side, so I don't have to worry about positive or negative here. We found omega to be 8 pi, and it's times time. So as we finish up our equation, wait, there was one more thing, right? Exactly 3.45 seconds. So time is in seconds. 8 cosine 8 pi times 3.45. And we're going to get an actual position to deal with that. Okay, so plug that in your calculator and you should be all set. All right, number 5. Let's see. So we're at 0 centimeters, right? 0 centimeters. So we get a spring, we get this weight on it. And if I go in order, it looks like it's going to go down and then it's going to come back through that equilibrium and go up. So it's oscillating back and forth. So you may have done this in physics class, just dealing with not only how far does a weight make the spring spread out, but also deal with a few more things. So I see that we're going to be between 5 and -5. So its maximum displacement is going to be that 5, and this is listed in centimeters. Okay, and I noticed that find the modeling equation if it takes 2 seconds to complete one cycle. So it's going to be 2 seconds equals 1 cycle. Okay, so the period is 2 seconds. I'm going to make that 2 over 1, and that should be equal to 2 pi over w. All right, so we're going to cross multiply. 2w equals 2 pi divided by 2. So omega, I don't know why I keep using w, is pi. All right, so I have omega. I have a maximum. Remember, this is going to be the amplitude, which is a, which is 5. So I think we have everything we need here. Okay, so we have 5 sine, right? Because we're starting at that 0, 0. We found omega as pi t. So we can say our function based on time is 5 sine pi t. Right, now, it does go down first. So this is one where it should work either way, but I'm going to put plus or minus. So we could start at the positive or the negative, because it's going to replicate that as it springs back and forth. But that should be all we need with this one. Okay, so remember, we're going to use reciprocal function because periods and frequencies are reciprocal functions. I'm going to try not to say inverse, but I may eventually say inverse by accident. But that's what we're going to deal with. Okay, so we're going to take out phase shifts. We're going to take out a few of those translations, and we're going to use calculator values as we work through it.